Welcome, boys and girls. Class is in session. So this is going to be a fun one. People know that we try to not stay too pigeonholed in any particular category within our Rising Tide Foundation lectures, but we do try to encourage people to think interdisciplinary from an interdisciplinary standpoint and think about how do different aspects of human knowledge intersect. And so I thought today, 2026 is opening up. We're being told all of a sudden all of the standards of science that we've been told we have to adapt to don't really matter anymore. Bill Gates is coming out saying that global warming is not such a big threat any longer. Whole industries that have been built up around reducing human-made CO2 are finding themselves in a weird position now, where it seems as though there's a recognition to a certain degree that there are many holes within the thing that we've been told is climate science. And the question now of what is a real science of climate? How does climate change? Is carbon dioxide falsely labeled as the culprit of all of our problems, or is there a bigger picture in play, a more beautiful story about the nature and the science of climate and change within the Earth and maybe the other planets more broadly? These are all very important questions that have been sidelined over many decades. And Rodney McInnis is somebody who maintains a fantastic website. It's Climate Bell. I want to say climatebell.org. Rodney, am I right?
That's correct. Yep.
Okay. It's a great website. I suggest everybody put it on their bookmark this site. It's got a lot of resources for people who want to get a better handle on what is a responsible approach to thinking about the science of climate, and specifically the greenhouse effect more specifically. And Rodney agreed today to share a lot of his considerations, his findings, based on just raw data analysis that anybody could look at, but not many people look at it competently. And Rodney's done an immense amount of work. So I thank you so much, Rodney, for taking the time. And after Rodney's main presentation, like usual, is finished, we're going to open up for a bit of dialogue, some Q&A, and just pop your names in the chat box, and I'll call upon people accordingly. And without further ado, Rodney, the stage is all yours.
Thank you.
All right, yeah, we're doing the screen share. Yeah. Great, we can see that. So just make it a full screen there, and we're good to go.
There we go.
Excellent.
All right. Well, thank you, Matthew, and thanks to the Rising Tide Foundation for your interest in the Climate Bell R&D. My R&D, I don't consider opinion. It's based on detailed computations using established physics with official data sets and validated with official measurements. My unique value add is the modeling of the greenhouse effect, designing and coding a tool I call GHG Lab, and solving the feedback effects. So my short background is, let's see, I'm having trouble scrolling here. Just give me a second. Sorry about that. Get used to it here. Bear with me. This is only my second presentation on Zoom, so I'm a little bit rusty. My short background is a BSc in Physics from UNB. 1 year working for the UNB as a research assistant in a CO2 laser lab. I did a Master's of Applied Science at U of T, specializing in semiconductor physics. And then my first career job was 15 years at Bell Northern Research and Northern Telecom in various roles, including a semiconductor chip foundry. I did 2 years working for a small company, directing a team developing the first Transmeta processor-based server. Transmeta was a new processor manufacturer competing with Intel. And then finally, for over 2 decades, DelphiTech developing exterior LED lighting. The Climate Bell initiative started by accident in 2022. And since then, I've spent 3 to 4 years of full-time effort on this personal assignment. This is my second presentation, and I've done 1 interview so far. So let's see. All right. And I'll get used to the clicker here. Okay, before I get started, I just want to acknowledge some people I've benefited from over the last 4 years. They've helped accelerate my progress in various ways with technical information, confirmation of certain physics and modeling choices I made, and encouraging me through their kind comments and donations. And for the anonymous organization on there, they wanted to keep a low profile, but liked my work and paid for my way to a conference so I could network with others. And there I got to meet in person Dr. Joseph Fournier, who I've come to respect for his excellent scientific perspectives. The anonymous person did the new website for me, and it gives me hope for youth. He's in his mid-20s working for a high-end marketing firm, and he learned of my findings and was startled to have been told otherwise all through his youth. A few days after he had interacted with me, he got a hold of me and offered to upgrade my website to a professional standard on his own time. And it was a spectacular transformation, one that he easily must have spent dozens of hours on and perhaps more. So I'm immensely grateful for his charitable kindness, as I would not have been able to afford his firm. And I'm not mentioning his name so he spared potential climate controversy in the workplace with his current or future clients of his employer. So my views on climate change have shifted over the last 25 years, from first believing the proponents had good faith scientists understanding it, to becoming skeptical perhaps about a dozen years ago, to becoming annoyed with its alarmism and diversions of vast resources in the last few years. Those people now threatening freedom, food, and energy, leveraging alarmism, to me is unacceptable, especially when it is enabled by faulty or recklessly negligent science and perhaps even blatant corruption. So my inspiration for starting this was a video a friend sent of Carl Sagan presenting to Congress in 1985. I've quoted a few lines there from his talk. But essentially, as highlighted in the red text, what I took from his words is assurance that the greenhouse gas effect is well understood, claims that they can calculate it accurately, and a prediction Earth's temperature would rise during our current century by several degrees Celsius. I provided the YouTube channel link for the long version of the session. It's about 2 hours where Al Gore speaks, then Sagan, and then other scientists. So having a physics degree, I saw doing a back-of-the-envelope calculation of temperature rise for GHG level as a personal challenge, just like somebody else would do a crossword puzzle or something like that. I had to admit to myself back then I had a poor understanding of GHGs. About all I understood was that they absorb energy by vibrating, and through some mechanisms I didn't understand at the time, they heat the Earth's atmosphere. My tendency has always been more of a doer than a reader. And problem solving had been a frequent, satisfying activity in an over 35-year career in technology. So the combination of a physics problem with some computations was compelling to me. I also was naive enough to believe that I could find a wealth of clear information on the web that would rapidly assist me in doing the exercise in a few days. I never realized at the time it would trap me in a drop everything else obsession. And here we are a few thousand hours of work later. So first, a quick view just for perspective on where we are in our temperature swing history across a few ice ages during the last 500,000 years. The upper two graphs use ice core samples as proxies to extrapolate and compute the temperature over those periods. These swings in temperature are as much as 6 degrees Celsius higher and 8 degrees Celsius lower than our present-day temperature shown in the dashed lines. Over the last 20 years or so, as I see it, two camps have emerged regarding rising greenhouse gases and climate change. Camp 1 and Camp 2, and I list a few attributes of each. Camp 1 says that there is no need to do anything about it, and Camp 2 says we need to take action. Oops, sorry again. Got to get used to the scroller. So this presentation is as a result of 4 years of R&D, and while it might not persuade any in Camp 2 to convert, it is designed to bolster the resolve of Camp 1 by equipping them with multiple proofs that their understanding is correct. This is so they can attract new enthusiasts sharing the good news with those who are hoping to hear it. With this presentation and those who may see it in the future, I need to engage both lay people and scientists. For the scientists, I'm looking to initiate a non-standard peer review in the near future. I'll talk a bit about the science here today, but to keep it interesting for all, I'll not dive into fine details, just mention some of them in passing. For the lay people, I'll explain the greenhouse effect at a level where you may understand it better than many scientists who make it overly complicated and lose their way. And believe it or not, it is actually quite simple from a modeling and simulation point of view. I'm also going to talk about the problems with the science and the behavior of various arms of the establishment. I'm not here to whine about it, but to express my deep concern for how off the rails things are. My task isn't to fix them, but to equip and hopefully inspire some viewers with the insight and confidence to band together for strength. The problems around climate change appear to be an escalating set of severe, costly, and restrictive mitigation actions underway to curb greenhouse gases. These are being implemented by various arms of the establishment based on reports coming out of the organizations such as the IPCC, the Intergovernmental Panel on Climate Change. Their guidance has wide-ranging temperature predictions from rising greenhouse gases for this century, values they say will be dangerously high. From my point of view, their lack of precision and their shifting estimates suggest their science and computational models are poor. Climate Bell was created early on when preliminary calculations revealed the general narrative on climate change was significantly overstated. It was created then in hopes of fixing any errors in the science, and so contribute to defending the security and affordability of transportation, freedom, food, and energy, all of which are critically important to humanity. GHG Lab was developed, and all related feedback effects were examined pertaining to Earth's temperature changes. GHG Lab is available to any individual or organization that wants to join in that defense by showing an accurate computation for the effect of rising GHGs. It not only does the computational work with its plots and easy click adjustments, it's a great GHG teaching tool. And I think many, especially those with a technical understanding, will find it very educational and fun to use. Many famous physicists quote, Richard Feynman says that science is the belief in the ignorance of experts. And since Carl Sagan got me into this with his assurances in his 1985 congressional talk, and to be fair, I don't know who did calculations back then, or if he took someone else's word for it, but he did provide counterbalancing warnings in his books and his interviews that I greatly respect. One of them was, one of the greatest commands of science is mistrust arguments from authority. Too many such arguments have proved too painfully wrong. Authorities must prove their contentions like anyone else. Since the whole climate alarmism is built around limiting GHGs as humans are blamed for the rising levels and supposed dire consequences from those levels, my original target was to compute their effect on temperature, and then later expanded the target to include the feedback effects. I still need to remind myself from time to time, like in the Star Wars movie, to stay on that target because that is where the wiggle room gives the alarmist traction. This is some, I guess I'd call it a marketing plan for freedom enthusiasts. And basically, this is the grassroots marketing plan to cross the chasm. And it's borrowed from a book written by a fellow named Jeff Moore many years ago on getting society to adopt new technology. An example might be thinking of going from the rotary dial phone to the touch-tone phone, as to give you an example of a technology. And the labels in the diagram are Jeff's, not mine. And I only came to this notion as to my target audience this spring when I attended that first conference. And I'd been on social media for over 6 months, doing posts and explaining things to people. And as far as I could tell, I'd converted nobody. And I got, various rebuttals and so on. So in this diagram, the innovators are going to be the scientists that peer review my work. And then the early adopters are going to be the people that have sensed many of the problems with the climate science and are fed up with the burden and harms of existing and planned mandates, and with some thought embrace the new information to bolster their position and spread the word, so others with an early adopter mentality engage. Some would say that I'm just preaching to the choir, but I would say that I'm engaging or equipping the choir and bolstering their confidence that they were right with proofs that help their enthusiasm. They're not pack follower. They don't have a pack follower mentality, nor are they stupid or foolish. They make up their own decision based on judgments that they make with what is presented to them, without the need for approval from others. Once a critical mass is achieved, the chasm is crossed, as Moore explains it, and begins to creep into the early majority, which continues to spread and goes over the hump. And I've sort of defined that. The early majority are less likely to make a decision on their own. They need to see the momentum. The late majority are reluctantly conceding. And the laggards are stubborn skeptics and people that see opportunity for themselves in holding the narrative. And so I thought of if there's people perhaps listening to this now or seeing the rerun of a way to recruit early adopters, and there's probably different ways to do it, but basically you're going to want to look for their open-mindedness and their ability to make a decision. I'm just going to move the screen here so I can read that. So I thought of one question, and there's probably several of them that are equally good, but you ask a person if they learned that the claimed concerns from rising greenhouse gas levels are wrong and not a problem, and if you ask them if you learned that proof was readily available for any objective and competent physicist to scrutinize and that it was so, would they be happy or sad about that question? And that's the reluctance to engage in an honest way. And to spend time with those other groups is really a waste of time. I've done a lot of interactions, and I'm able to field all the questions and challenges, and yet, as from my point of view, I didn't convert anyone, or at least nobody admitted it in those social media engagements. Let's see here. So I put this slide up on problem-solving surprises. And basically, those are two wire puzzles, and they kind of look simple, and you may have seen these before online or played with one yourself. They're fun videos to watch, actually. There's a store that sells them. And they look easy, but they're ranked by the manufacturer at level 10, where 10 is the most difficult level to solve. And borrowing on these examples as paradigm, in general, sometimes problems look easy but are difficult. And conversely, sometimes problems look difficult, but they're much easier than they appear or people presumed. And once you have experience in solving one difficult puzzle, it teaches patience and confidence that one might be able to solve a new puzzle. And if one can solve it, can't solve it, seeing the solution removes the mystery and exposes any mental blocks that prevented one from figuring it out on their own. And on the other side, this is called the tiling problem, and it was solved, I think, 3 or 4 years ago by a fellow, David Smith, in the UK. And it's called the one tile, or it's been named the Einstein problem, having nothing to do with Albert Einstein. Einstein, I guess, in German means one stone. And the neat thing about this story is mathematicians tried to solve this problem for over 50 years. And then along comes Dave Smith in the UK, and he's just an amateur math hobbyist and doesn't even have a bachelor's degree from university. And once he thought he had a solution, he reached out to mathematicians and computer scientists. One of them was University of Waterloo, to effectively do a peer review of his work. And they worked on writing a software program to validate his finding. And while they were working on proving that, he found another one, and then he realized that you could do fine adjustments on the form and create an infinite set. So nothing was found for 50 years, and there's actually an infinite set of solutions out there. And this video is a physicist who does a really nice job. It's an inspirational story. And so I've linked videos for the two wire puzzles and her video in my, whoops, there we go again, in the bio section of my website. Let's see here. So they're in the bio section of my website for a purpose, and that is to help people keep an open mind and not prejudge things. So there's certainly vast numbers of physicists with more academic experience than myself, and also have a much deeper understanding of atmospheric physics than I do. And all of this is fine, but it actually isn't necessary to solve the greenhouse gas problem. And the numerous challenges, and there were lots of them about my credentials I received over the last 15 months and social media engagements, forced me to reflect on what I thought my advantage have been. And I came to the conclusion it was primarily two modeling and simulation experiences, each multi-year I was fortunate enough to have back in the 1980s. And these taught me to describe on the right-hand side. And I'll explain, I go into a bit more detail on my bio on the website, but I'll explain the two solutions. One was my graduate work at U of T, and basically, and I'll be talking about this a little bit later in the peer review critique, but it was a modeling and simulation problem, an industrial problem that had been recognized perhaps 15 years earlier. And there were numerous engineers and scientists that have worked on it in industry and also worked on it in academia. And I basically came up with an innovative solution, finished my graduate work, started my job. And I didn't publish any papers when I was at U of T, and I really wasn't interested in publishing a paper, but I kind of wanted to present it and get some live feedback from people. So there was an international modeling and simulation conference in Pittsburgh, and I think that was '86. And I presented it there, and I hadn't been into the literature for about 3 years, and I was just kind of curious. And when I presented it, the attendees, there was a good long discussion afterwards between them and me, and it basically, by the discussion, nobody had seen the solution before. So it was, I guess it was the first time it had been publicly explained, and that was satisfying. And then about a year later, I got an assignment at Bell Northern Research. Their semiconductor foundry that I worked in basically in the design side, not in the foundry itself. They had a major problem where some designs coming through would fail. The simulation said it would work, and the first samples were failing for a timing reason. And the consequences of that were a redesign, or had to investigate and then fix the design, which might be a project setback for a few months. But it was a major thing for Northern Telecom owned the foundry. It was $1 billion foundry. In today's dollars, I think that's about a $6 billion foundry. And the problem is there were two annual trade shows, one in Germany and one somewhere in the US for telecom, and buyers would go there to select a product to build out a new network, like buyers like AT&T. And if you don't have your product there for that buying decision, they might start with some other vendor, Lucent or something. And if it worked in their first procurement, they're going to spend 10 years building out that network with purchases every year. So the consequence of a single chip design delay could be $100 million lost to the company. So the company was under threat by the board of directors. The foundry was under threat. And there was turnkey contract manufacturing companies that would guarantee the simulator would match the silicon. And so the company was thinking they'd do new designs in the contract manufacture. Anyway, a couple of years' work, and there were multiple problems I found. And so that one got solved. But that one was different because I knew there was a solution. I just didn't know if I would find the problems and I'd be the one that solved it. And then this wasn't really a modeling and simulation problem solving. It was just an implementation. But for my LED lighting, I wrote a simulator. It took me only a couple months, and solved a complex arbitrary electrical network so that the people out in the field could know that their installations would work every time. And that gave me sort of a focus on the excellence of Excel in this mathematical construct. So it was the logical tool for me to pick up when I did this. And one of the challenges was, well, I'm not a meteorologist or climatologist, but it turns out that doesn't actually matter. In fact, it might have been an advantage that I didn't have a bunch of training in that area and start using some technique to chase the energy around in the system, as opposed to recognize that it's an orthogonal solution and it's a pure physics problem, and one that's not that difficult once you recognize the partitioning. And this is the peer review. I don't really want to explain it in detail. But basically I'm going to write a white paper before I can start the review. And for those that want to do the data sets, it's really a modeling challenge. That's where the climate scientists have fallen down. They can do physics calculations just as good as anybody, but the modeling to set up before the simulation, that's where they go astray. And the purpose of a peer review, it's not so much for the early adopters. It's more for winning the early majority and the late majority in that adoption bell curve I showed you. And it's also confidence for the industries to band together. Once they have proof that's validated from scientists that they trust, could even be just be one scientist that in-house or someone on the outside, that if they say this makes sense, then they're for it. And the problem is with the large industries now, like oil and gas, if they're already into the ESG game, I presume most people have heard of that, they're playing a game of musical chairs to be some of the last companies standing. And so they might be a little reluctant to change direction when they're vying for favoritism from the powers that be. So maybe it's the large investors that get on their case, and maybe a large investor wants, a peer review before he goes and starts chasing the board of directors or something. Anyway, the thing is to eliminate the wiggle room. And so I'm looking for physicists that aren't compromised by academic worries and funding worries. I want them to have a visible presence online and some industrial connections, and we'll be in communication. And I also want them to be bold to provide a visible review and a quotation. And so the selection, I'm looking for them now. I've got 2 already. The selection will be after I've got the white paper done and I've got a sufficient number to select from. But I'd like it to be, not most peer-reviewed papers are reviewed by 2 reviewers. I'd like it to be, let's call it a jury of my peers. So 12 would be good if I can get 12 that are willing to do it. This is just more of a little bit of poking fun at the bear. I call it stupid stuff in climate science. And the first 2 really are stupid. For the forest fire stupidity, imagine a person getting hysterical about a hot cup of coffee on a newspaper and saying paper is flammable and you'll burn the house down. So when they say a 1 degree rise is the cause of forest fires, it isn't the case. More reasonable causes would be a drought that dried the forest, a summer-long drought, or leaving a bug-infested set of dead trees standing. Arson is a good one. Not clearing out brush are common reasons. And you've probably heard the global boiling stupidity. Today I'm going to show you computational proof that all the ocean warming is due to a reduction in cloud cover. And that should satisfy that. And this one's a little bit trickier. I call it an insidious misdirection. And I think it's the worst one. And it's an insidious misdirection because it easily tricks us all on our senses and memory. in terms of global warming or climate, greenhouse gas, climate change induced, causing more severe weather events and climate events. I call it stupid because of the science. The energy in the Earth system is only increased by 0.35% for a 1C rise in temperature, as it's proportional not to the Celsius temperature, but to the Kelvin, which is Celsius plus 273. So that should make no noticeable difference in weather events, and this is confirmed by those who have examined weather event records. Those records show no protracted trends in severe weather event frequency or magnitude. The records go back over a century. On the right side, I speak about the roles of CO2 in heating, how the energy into the planet and out of the planet is a steady flow. It's not. That's why you don't chase the energy around, which is a tendency for weather people trained in weather and climatology, which is the right thing to do for that discipline, but it's not related to the physics of the greenhouse gas effect. And also how we think of the flow staying within the Earth system as a zero-sum game of energy transformation. And those are sort of basic elements in doing the modeling properly so you can do the simulation. And now a little bit of complaining about the climate change industry. So some bad, the slow, and the ugly, I call it. So this one, I made some observations. This is prior to me starting this work. During the pandemic, I guess I was on board for about 6 months with the establishment narratives, but it became more and more, let's say, ridiculous. And by the time in 2022, which the pandemic was winding down, I had accumulated a lot of bitterness about some of what I perceived as the mistakes made along the way that others had expressed concern about at the time, and then more people realized it. So I wasn't going to bring this up, but this is a while ago. I went looking for, is there any arm of the besides things like the WHO and the World Economic Forum that glommed onto both the pandemic and the climate change for reasons that they have. Excuse me, I just got to wipe my nose here. So I went looking for some other arm of the establishment where they brought pandemic and the climate change together, and I stumbled into this beauty, and it was a presentation, I think out at UVic or UBC from a Bank of Canada executive in August of 2020. And in the first two slides, so first of all, he embraced the Great Reset, which had just come out in July in a book form, linking COVID-19 for some strange reason to the Great Reset from the World Economic Forum. And this is the first two slides. That's the first slide, and this is the second slide. And I observed many similarities, but basically they embraced the Great Reset, which I see as a scheme from the World Economic Forum that appears to extract all our intergenerational wealth and puts it into the hands of a few, making humanity totally dependent on a serf-like model. And then they don't even seem to be questioning the actions of the pandemic or climate by various entities in the establishment. And in that second slide, they refer to the pandemic as an opportunity, but they didn't clarify for who, because most people would most people and most companies didn't see it as an opportunity for them. So that got me, let's say, a little bit confident about speaking about some of the correlations I saw in the behavior of this establishment. And it doesn't mean my view has to be your view. You may have a different view of how the establishment handled the pandemic. That's up, that's your privilege. But this is the I wrote down a list of things that I saw as similarities. I guess I'll read the list. I could just read a couple or three of them, but First was the fear propaganda pushed relentlessly by governments and media at all opportunities to do so. False and exaggerated statistics and false correlations are used to reinforce the fear. In both of them, a cult-like following developed that aligned to the establishment's fear narratives. Their predictions and promises fail in profuse ways, but it doesn't stop them, and all arms of the establishment continue in unison. Only one narrative is permitted by the establishment, and no public debate is allowed, even by topic experts. Even when any of their science is exposed to be false by those with expert scientific acumen, the establishment won't reason it out. The name calling in both things, anti-vaxxers and climate deniers, lockdowns and which was and they're planning it for the climate as well, and restrictions are sold as being good for the person, good for other people, good for the children, good for the elderly, or just for a better future. Whether part of the establishment or not, those lecturing or chastising others frequently don't follow their own advice. Much harm has been done to youth physically and mentally from needless worry and restrictions, but the establishment won't alter their agenda to mitigate harm. The appeal influence of authority gets the establishment majority compliance. And I don't know if any of your listeners are familiar with it. I went looking for reasons and stuff during the pandemic. How could all these people charged with trust in the establishment be so ruthless? And I came across this, I think it was in the 60s, Professor Milgram at Yale did an experiment to show how far people would go with authority. Would they cross a line out of respect for authority? And it was I won't. You can look it up. I don't want to waste the audience's time explaining it in detail. But basically, the professors reasoned that 1% to 3% of the participants would give their patient, let's call a patient, an electric shock into the lethal range, and it turns out 70% did that, which was a complete surprise to the professors running the experiment. Continuing, bribery and coercion are used as tools to build an even larger majority compliance from individuals and corporations. Health organizations who failed multiple ways in the pandemic also try to worm their way into the climate change hysteria to gain power over that domain by making it a health issue. They appeal to recruit self-righteous bullies outside of the establishment who will do their bidding and chastise others who will question any narratives. This was mostly in the pandemic, but it's also, comes across maybe not directly stated, but the narrative we're all in it together is the selling pitch touted by arms of the establishment like governments when the establishment frequently exempt themselves from the same pain they impose. Human and charter rights are dismissed by various arms of the establishment. They breach the trust of their positions that people expect them to uphold, while the law and the courts do nothing to protect them, the people, that is. Economic hardship for most outside of the establishment, yet those in the establishment feel little or no pain and may even profit. The establishment gleefully brags about it being a severe threat, but also claiming it as an opportunity, and later often clear motives beneficial to the establishment and the colluding industries become obvious. Large corruption often found in schemes where they spend vast amounts of money on fighting either threat. And when the failures are exposed, there's no apologies, meaningful investigations or criminal charges against those in the establishment where breach of trust or corruption has occurred. So that's my rambling list of 20. There's probably a few more. And so this is kind of how my view changed. So, there's these, I call them arms of the establishment here, and then there's the people outside, and there's the industries outside. And so I drew them as little clouds, and there might be some loose connections between them. But it was kind of a hodgepodge of, people believe that the media would challenge the government. But once the establishment sees opportunity for themselves, it's a very tight-knit group. And the coordination within that, there's some unknown cabal, I think, that decides what the agenda is. And and everybody moves into lockstep. And so the people are given information, instructions, and commands. And there's coercion inside the establishment and opportunity promotions and so on. Then outside, it's the same type of thing. And the coercion for the industries is really compliance with ESG and DEI. And this might might not sit with your view of things, but I thought about it a lot, and it's a model that I think applies not necessarily to every situation, but certainly when the establishment sees opportunity, which appeared to be the case with the pandemic and appears to be the case with the climate change narrative. And so since you're not when they're in that mode, they can't be reasoned with. It seems the only way they drop their stance is to have no wiggle room left, which occurred in the late fall of 2021 when the people and companies frustrated by the mandates were able to collectively show there was no merit in them. Finally, with the Omicron spread, then the establishment relented on the mandates. So the Climate Bill R&D addresses the areas seen as remaining wiggle room. The IPCC, these are going to be computational highlights that are in this presentation. The IPCC uncertainty in defining the doubling of CO2, we'll be explaining how peer-reviewed fails, identifying the flaws in other greenhouse gas models, explaining nitrous oxide, methane, and carbon dioxide with accurate and precise computations from GHG Lab. I'll be showing how GHG Lab was validated using official measurements. I've gone into, I spent a year and a half on using NASA's satellite data. They'll give you an account. You just say you're an independent researcher. Downloaded a lot of data sets and done analysis to address the feedbacks. And as I said earlier, I'm going to be showing you how the ocean warming was calculated and has nothing to do with GHGs. The ratio of the warming from the change in cloud cover when I computed that and compared that to the increase in warming from GHGs on the surface of the ocean, it's a 477 to 1 ratio, 477 the cloud change and 1 the greenhouse gas change. So I'm attacking peer-reviewed papers now, and this comes from my graduate work at U of T. And this is a diagram of what I worked on. I don't need to explain too much. It's a simplified diagram. These are resistors, and these are bipolar transistors. The actual transistors in the CMOS technology are what's called MOSFET transistors up here. But you get this parasitic effect. Parasitic means you didn't want them, but they function that way inside. And this has a name of a component in. When you do it, when you want that component, it's called a silicon controlled rectifier. And what it is it's a switch with a gate signal on it. When you apply a gate signal, it locks up in a very low resistance mode. And those are devices that are very useful. And they only unlock when you remove the power source. So this effect had been discovered in the 60s and was getting progressively worse because people were packing smaller and smaller transistors closer and closer together. And as you do that, the feedback effect here, and it's a positive feedback, meaning once it turns on, it latches and turns on as hard as it can. It was limiting the size of the density of CMOS chips. And when I was working on my graduate work, a CMOS chip might be 100,000 transistors. Now they're tens of billions of transistors. And without this thing solved, you're limited in how many chips you can get on a die. And the problem was, I'd been collecting papers. I started in '82, and I went back perhaps 7 or 8 years. So you go down to the library and you look for papers and you photocopy them. So I accumulated 106 papers as I started working on my graduate work. Let's say I accumulated most of them in the first year and maybe a bit more in the second year. And I started doing my measurements right away. I had samples from Northern Telecom to because they'd funded my lab, I guess, and provided samples. I was the grad student working on it. And basically, I started measuring, and I measured it the way a silicon control rectifier should be measured to get the full curve. And what you'd want to do, you current limit this. So this is a voltage current curve. The current goes too high, you burn the device out, and you have to trigger it. But the power supply is out at 3.5 or 5 volts, and this is typically around 2 volts. So how does it get triggered? You need a transient event that temporarily turns on these transistors. And the reason, even though this is hooked up to 3.5 or 5 volts, the reason it gets to here is because the little die tracks, the little aluminum tracks on the chip, because they're so small, they have inductance and resistance. So basically, even though it's hooked up to 3.3, it can get down to 2 in a rapid transient event. And this region here, if you want to call it a portal, to get into latch up, all the latching events has to come through this portal, right? Because that's when those transistors turn on, and finally there's enough current to in a very rapid time, billions of a second, to have a different voltage here than out at the pin of the chip. And then what happens, you want to current limit this, or you're going to burn out your sample. So you put a resistor on your power supply to keep it to a maximum current. And this travels around here in about a few billionths of a second as these things turn on, very small geometry. And then it sits up here. And then the question is, if you want to characterize this, you've protected your chip here, and now you're going to change one thing, the current or the voltage. And believe it or not, only 4 papers changed. You have 2 choices, current or voltage, and only 4 papers change the right one, the independent variable. So the current is the independent variable. The voltage follows that. So if you move the current down, it'll follow this full path. And if you're not characterizing this region, you're never going to simulate the thing properly. Not all the papers, not all the 104 did measurements, but a good many of them, many dozens of them, and they swept voltage. And so they ended their measurements here and missed the whole region where the modeling is important, where these things turn on. And I only went back to count papers after I finished my graduate work, kind of thinking I didn't see many papers that measured this. And my reasoning is not corruption. Everybody wanted to solve it. My reasoning at the time was perhaps the research scientists, the grad students, the postdocs, were just following some of the first papers that measured it wrong. It's remotely possible that they knew they couldn't model this, and they knew they should have measured it over here, but they didn't want to show that their model stopped here, perhaps. But I have no evidence of that. So anyway, that was my first experience where peer review failed. So they weren't saying no to measuring it right, but they were allowing incorrect measurements in. So the peer review wasn't discriminating on that. I'm not sure what they were discriminating on, but it suggested to me that the peer reviewers didn't know enough to review the thing properly. So it was okay. So this is my understanding. Keep in mind, I've never written a peer-reviewed paper, just a conference paper. But the editors, there's some controversy in the climate stuff about, there's a guy, Andy May, who cites some cases of editors who conducted a peer review, and let's call it a heretic paper, passed the peer review with the peer reviewers, and the editor published it and got fired. So there may be a little bit of a bias there, I'm not sure. But typically, I'll use the word cherry picks. That term has been thrown at me lots of times in social media, and I'll show you the plots in a bit where I was accused of cherry picking things. But I'm going to use the word cherry pick. He cherry picks 2 reviewers with subject matter expertise, in his opinion. And if there's unresolved controversy, the editor sorts it out as being the 3rd reviewer or picking another one. So the peer review can be weak and could be corruptible, and may be biased in some areas where there's research grant bias for political agendas. Yet the problem is lay people and many scientists put exclusive faith in the system to the rejection of other work and evidence that isn't peer reviewed. And as I say, I've been criticized, or maybe I didn't say it, but I've been rejected frequently in social media for not having a peer-reviewed paper of my work. And my thinking is, even if I spent the time and the non-refundable thousands of dollars to submit and managed to get my work published, I believe it wouldn't make a difference, as the criticism would no doubt shift to my one paper refuted by 100,000 others, or I didn't pick the right prestigious paper, a journal rather. So if one compares the peer-reviewed paper to a court testing of the truth, then I submit that the editor clearly is not the defense attorney, but they are the prosecutor. Now imagine a court case where the prosecutor picks secretly two jurors of his choosing. The author of the submitted paper represents themselves. The prosecutor also fulfills the role as judge. The authors of the paper, especially those in academia whose status, employment, and research grants are determined by the count of published papers, are put in a compromising position of plea bargaining to please the prosecutor to receive the favor of being published. That is the status quo. And I think, before the internet, maybe this was the best that could be done, or maybe it could have been a little bit better. But I submit that the time has come for this veil to be lifted on the system, and some form of an open internet-based approach could be designed. But that isn't really my focus today. I'm going to continue on the weaknesses of the peer review as it pertains to climate research. Oh, this was something I did. I didn't do it till I started doing feedback effects, and it's a stupidly simple thing to do. And the reason I didn't do it is I jumped into doing computations right away. And this is the claim that the CO2 is the main driver of reverse temperature, and they have this correlation for the last 6 decades of rapid rise in CO2 and rapid rise in temperature. And the temperature rise is rapidly rising. I can confirm that with the satellite data sets. And the CO2, I don't think anybody's really challenging the CO2 record. And I call this the region of misdirection. And they say, well, there's your proof. You got these two things going in the same direction. And what they fail to acknowledge is 84 years before that. I drew this thing, and the people that argued with me, it really made people upset. They would like to drag this curve down, ignore all these up downs, and say, well, it kind of fits, like just slice right through here and ignore the trends. But I have the statistical uncertainty from NASA as well, and they give a 2 sigma, which is a 95% uncertainty. And this trend here, and this is not noise. This is centered temperature measurements. A centered measurement here with an uncertainty bar not drawn here. And then what I'm going is from it. This is an inflection point coming out of the 1880. And then there's a downward trend. This is the lowest point on this thing before it starts a trend upward. And that's the highest point on that trend upward, and then it comes back down in. It's centered to centered. And this is a 6 sigma drop. It's a 6.25 sigma drop. And 6 sigma is 99.9997%. A 12 sigma rise here, it's 100 point and a bunch of zeros, certain. And this is a 10 sigma, and that's 100 with a bunch of zeros, certain. And then it's a certain rise here. And so I tabled that, and these are the error bars, the 2 sigma error bars from NASA. And a lot of this has been challenged, not challenged, checked. There's what was it called? Berkeley Earth. They spent over $1 million to kind of confirm that the temperature record was right. I think even one of the oil and gas people threw in money to big oil and gas, Koch Industries or something like that. Anyway, so people were fairly comfortable with this. The climate alarmists are not challenging NASA's temperature record, and nor are they challenging this, but they can't reconcile this. This 84 years is evidence that CO2 is not the major driver of Earth's temperature change. It's absolute evidence. Unless you're going to say this is really messed up here and this is irrelevant, there's no getting out of that. And then one of my computer science friends looked at that curve and he goes, yeah, you can make it simpler. So I drew it as candles. And this has been another one that I've published, and it really enrages people. And what this shows is parts per million rise per year. So all these blue candles are CO2 rising, and it rises a little bit in this first trend, okay? And then it rises a little bit more in this trend. Then it rises quite a bit more, and this is the fourth trend, and it's rising a lot. And I plot it against change in temperature per part per million to normalize it against the change in CO2. And so this is going up a bit, this is going down a fair amount, and this hardly goes up a bit more, and this is going up quite a bit, and this is going up quite a bit more, and this is going down a bit, and then this is going up a lot, and this is only going up a bit. So this is, from my point of view, this is the gateway to any non-scientist knowing that it's proof that CO2 can't be the major driver of Earth's temperature rise. And this is a complete failure of peer-reviewed papers again, because the peer-reviewed papers, many of them claim that our emissions are, they say it either directly as CO2, or they say it as our emissions are a major influence on the temperature rise and climate change. And those papers that make that claim do not refute the temperature record, and they don't refute the CO2 record. So I view this as your gateway for any non-scientist to see the claim about CO2 is wrong. And yet, 80,000 peer-reviewed papers didn't prevent such an obvious and fundamental flaw from getting published. In fact, they might have even encouraged that. I don't know that for sure, but it's a possibility. And then the IPCC, they started in 1988, about 3 years after the Senate hearing that got people excited about rising CO2. I'm not sure if they were directly formed. I don't know the history there, whether they were directly formed because of that or they got formed for some other reason to study this. But I would have thought they would go back to the people that gave testimony there and find out who modeled what and who checked it. I don't know. This is from their AR6 report, which I believe was 2021 or something like that. But this is the range for doubling of CO2 that they're working with some 33 years later from their formation on their sixth report. What did they find out? Did they go back? Did they ask those people? I don't know. Another startling thing is the data sets I use, and it was CO2 and water vapor, and they had profiles up through the atmosphere from aircraft measurements and from weather balloon measurements. So they had the data for profiles of CO2 and water vapor. The absorption databases I use are created originally from U.S. Air Force. It's called HITRAN, and it was formed in around the end of the 60s. And so the data sets for absorption of detailed absorption spectra for water vapor and CO2 were available maybe around 1971, 2, or something like that. And then there's the compute power, because what I'm doing is a piecewise integration across the spectrum, very fine-grained, because the structure of the absorption spectrums are very fine-grained. You know, it goes up and down quite in very narrow ranges. But a compute power of a mainframe computer in 1980 had that ability to do what GHG Lab does on a laptop. So effectively, there was no reason, if someone had done the work properly, there was no reason for alarmism in 1985 or the start of this from my point of view. And using their way of looking at papers that they will accept and rejecting some other ones, they have this distribution from, they think it's between 2.5 and 5, or, sure thing between 2.5 and 4, sure thing between 2 and 5. You could throw out the fringes. But when you actually compute it with GHD Lab, you get 0.48C, plus or minus 10%. And it includes the water vapor feedback effect, which they worry about. They don't quantify it because they haven't calculated it. But it's included in GHD Lab because it's the change in the evaporation, more water going into the air as the temperature goes up. And I'll show you how that's validated. So anyway, they're, grossly high in their, and grossly broad and grossly high in their latest report. So this is another thing. I'm not going to name the two provinces, but on 3 occasions from August 2023 to March 2025, I approached 2 provinces, I'm not going to name them, who had significant industry effects from climate mandates. And I thought these will be the 2 most likely provinces and they were spending a lot of money on mitigation. They were essentially sitting on the fence, playing both sides of the fence, appeasing the alarmists with their mitigation expenses, at the same time wanting to, support their industries that would be affected by the mandates. And I thought, well, the reason this timing, and I approached multiple significant people in each of the 2 provinces. And this came when I first published my first version of GHD Lab. I finished GHD Lab in the spring of 2024. There's been minor features since then. This is after I did my first presentation. So I thought I'll reach out again. They can watch my first presentation. And both times I got polite acknowledgement received by these people, their offices. And then I did this after what was it? I'm trying to think the event. Anyway, it was finishing a significant amount of feedback effects, so I could speak with some certainty about the feedback effects on temperature rising. And anyway, this time I got a response from one of them. So everything was polite and acknowledged, but this time I got a big long letter, and I'm quoting this, not mentioning the province, and you can read it, but it's basically, we're following the IPCC and we believe it's a significant problem and it's affecting weather events and irreversible changes, and we need to, limit our. So it was basically me trying to reason with the establishment, and just like with the pandemic, now I have some expertise in this area, but they don't want to talk about it. They're polite, but that's it. So that was sort of the last, and that is the last I'm going to try to reason with them. The good thing, I don't want people trying to guess and bother them. They didn't waste my time, which I've had 2 firsthand experiences many years ago with government wasting my time and wasting my money just to study something and write, weekly or monthly reports. So I'm pleased about their politeness, and I'm pleased with them not wasting my time. But I've concluded it is not the way. You cannot reason with when the establishment sees something in it for them. Is my conclusion. Maybe I don't have enough sets of evidence for this, but it's kind of the way I feel right now. And so the models, once you have a computational results that you can verify with measurements, and you have some solid ground to defend your methodology and your results, now you start to see the holes in some of the other models. So I spent many months in the first year and a half looking at other models, thinking, well, there's got to be something good there, and it just wasted time. it's kind of like a maze. You follow that model, you try to get some understanding, and then you realize it computationally it's going nowhere. You reach a point, and a lot of them chase the energy around in the system, like as if it was a weather simulation or a climate simulation. When, as I said before, the escape of the photons is orthogonal to that movement in that zero-sum game. So in these papers, I listed dozens, so that link up there will take you to it. And I don't go into it or dwell on them. I just make a one-sentence statement about models with this attribute, fall into, I'll call it a fundamental error. And it's not that they all have incorrect physics. It's that the approach doesn't lead to a computational result that is useful in computing the temperature rise for a change in GHGs, assuming that is what the modelers wanted to achieve. And I mentioned the dead ends. So some of these models are blatantly problematic. Like they separate out GHGs in what they call the radiative forcing, yet the absorption spectrums overlap. And what that means is that naturally occurring water vapor, of which we emit some in our combustion, but we wouldn't produce a measurable amount compared to all the water vapor in the air from evaporation off oceans, lakes, and off the land. So we can't change that. It is what it is. And that water vapor has a very profound, has somewhat of an effect. CO2 is very strong, so CO2 dominates, but it does do a suppression of CO2, but it's still a strong GHG. Methane and nitrous oxide are very strong GHGs, but it obliterates them, meaning rising methane and nitrous oxide are drowned out by the naturally occurring water vapor such that they're rendered impotent. And that's a very significant conclusion, because all the fuss over methane coming off oil and gas production, methane coming from farms, methane coming out of permafrost that thaws maybe for 10, 20 miles or something. All the methane fear is completely unjustified, completely unjustified. And nitrous oxide, as far as a greenhouse gas, it's a very similar story with that. So let me go to the next one. So there's going to be a bunch of slides here. The slide set's about 74 slides long, but it's not, a lot of them are going to go really fast because I'm just going to flip through them and point out a few things. This one, we can spend a few minutes on, a couple minutes maybe. This sets out some definition terms for people that need a little, you might have some scientific acumen, but they want a little reminder of some of the words, what they mean. These are two words that I borrowed for how I do the analysis. And I call scoping is usually less work, and it's less concern over absolute accuracy. It's something you want to get a feel for it to see if you really need to do a more rigorous investigation and dig as hard as you can. And so a lot of calculations here, scoping calculations do a pretty good job of saying, hey, that's important, or that's, basically irrelevant. Rigorous is, doing the analysis, the considerations for modeling the greenhouse gas, that was rigorous. GHG lab is rigorous. A lot of the satellite calculations were rigorous, but there were some scoping calculations around that helped me weed things out. A lot of stuff is in watts per square meter. That's the power flux coming into the planet, out of the planet. So it's a frequently used thing. Thermal capacity speaks to the amount of heat that can be stored, heat measured in energy, which is joules, per kilogram of material per change of 1 degree Kelvin, which is the same as 1 degree Celsius, just an offset, but this is a change in Kelvin, so it's the same thing. And then thermal conductivity, you have two surfaces, and you're measuring the flow of heat through a thickness measured in meters for a change between the two surfaces measured in Kelvin or Celsius. Light as both wavelength and particle property. So photon as a particle, and if you want to think of it wiggling at a certain frequency, creating a wave, that's a reasonable model to think of it. And so greenhouse gases, and this really says what it is. It's a gas that can absorb infrared photons of various wavelengths by vibrating and later releasing that energy by collision with another gas molecule, and thereby heat the air, or instead release that energy by emitting a new photon of light. That's giving up the vibrating energy that it captured from the photon. And then an unexcited GHG can collide with another molecule, start vibrating, and later release the energy by way of a photon or with another collision with a molecule. You might have heard the term black body radiation. It's basically a surface of liquid or matter, solid, has a profile, a continuous profile of emission over an infrared radiation range. And this I explained earlier is the difference between Celsius and Kelvin. All right. I'm going to talk about the Earth system in the sense of modeling this for the computation. There's going to be a bunch of slides here I'm going to skip through really fast, but just to touch base. And this shows the cloud distribution from satellite photographs and from satellite measurements of infrared. This shows the infrared emissions. And then this shows it with a projection that wraps around the planet. So that's why it's a elliptical or obloid thing. And what you're seeing here, there's three major convection loops, atmospheric convection loops going from the equator to the North Pole, and three the equator, and they're about 30 degrees latitude each. And the biggie here, you see a little wisps of cloud near the equator, but then the flow of the air, it comes over and then condenses and comes down again. What it means is that there's a lot of open sky 30 degrees north of the equator and 30 degrees south, and that happens to orient well with the sun. So a lot of heat is captured and a lot of it into the water that warms the Earth in the plus minus 30 degrees. And you can see from the infrared here, a lot of it is radiated. It really doesn't matter in terms of the capture or the release of this energy. And that's something that people kind of stumble on. This is NASA's diagram, and I've annotated it here with the line for top of atmosphere, some labels on some of the measurements here, and I've put them bigger here. But basically, this is the sunlight coming in, averaged over the surface of the Earth. It's only shining on one side, at a time, but it's averaged over the surface of the Earth, and that's a 10-year average. It doesn't change hardly at all. And then it comes in, and some of it's reflected off clouds. Some of it's absorbed by clouds and atmospheric molecules. So some of the heat is captured there, and that's 77.1. Remember that term, watts per square meter, the power flux. So that's the amount of energy being captured in the atmosphere. And then a lot of it gets to the ground, and that's the C, which is 163. And then D is the sum of these two, the reflected off the ground and reflected off typically clouds, but also off the atmosphere as well. And then E is the infrared radiation that escaped the top of the atmosphere. And you can see that they're very similar. B plus C is very similar to that. And the only difference here is a slight energy imbalance for a technical reason I'll cover later. But anyway, that's the Earth system. All this stuff that's going on here, evaporation, convection loops, precipitation, condensing the energy, evaporation, that's called latent heat going up. All this movement in here is that zero-sum game. It really doesn't matter. A lot of the models, they try to work with some aspects of this, and that's a dead-end path in terms of getting to a useful result. So you got the surfaces that are emitting black body radiation trying to get to space are cloud tops, not the underside, and surface of the Earth where there's a path to space. The path underneath the cloud, people say, well, the clouds heat up. And this is a common flaw, even for Camp 1 scientists, good scientists. They're a little bit confused between the greenhouse effect and the zero-sum game. And because a cloudy night is warmer, and why is it warmer? Where the infrared comes up, strikes the bottom of the cloud, and then it basically radiates back down. But that's not the cloud heating. That's the cloud not letting out the energy. The cloud is doing no heating there. It's the same energy. So that's just a circulation in the zero-sum game. Anyhow, let's go to the next one. And this shows a black body radiation. Let's say it's coming off the surface of the Earth. The outline of the pink curve is the ideal black body radiation. The purple jagged thing, that's what a satellite would see if it's doing a spectral analysis, sweeping across all the wavelengths. There's notches in it, lots of notches. And that's due to various things happening in the atmosphere, various absorptions, some greenhouse gas activity. This is greenhouse gas activity. This is ozone activity, the CO2 and the O3. And the pink that's showing is really the greenhouse effect. So what comes up off the surface is typically around -18 Celsius, and the average surface temperature of the Earth is about 15 Celsius. So scientists acknowledge, and I can confirm that yes, it's about a 33-degree warming from the sum of the effects of all the greenhouse gases. And this is your first glimpse at the tool called GHG Lab, and it looks a little bit confusing, but over to the right-hand side, you're going to see buttons for. So first of all, it does a differential calculation for energy balance, and it's doing the real greenhouse modeling with a detailed set of tables. There's 18,000 points for each greenhouse gas in the table, but it rips through very fast. And that equation that you see up there underneath the title, that's the key equation that's used in the computation. It's a piecewise integration of the energy. Over the right-hand side, you see a number of buttons. For A, A always defaults to 2023. That was my reference year when I first developed this. And then I don't update it. You can change the values in yellow. B is, I've got some presets. You can hit 1750 and compute the industrialization period. You can pick year 2075. But over on the left, you'll see on the very left, you'll see year B. You can put in any year you want up to 2100, and it uses the extrapolation from the greenhouse gas historical trends to extrapolate out in time. Anyway, this thing, you input your levels, you can change the defaults, you can turn off and on those little check boxes under FP times A and FP times B, allow you to toggle things. So it's very quick. You can just work with one greenhouse gas, see the effect of blending them, and hit run, and it will compute the temperature change for you in a matter of seconds. And over the right, you see copy to clipboard. For any experiment you run, it'll take a screenshot of all the parameters and what the results are. So if you want to put that in a report or something. So that's GHG Lab. Let's see. So I'm going to do how I'll give you 4 examples of how GHG Lab was validated. And the first one, there's a thing called the atmospheric window. And what the atmospheric window is, it's a region, and this is dominated by water vapor. It's a region where water vapor isn't as strong as it is across the rest of the spectrum. And that occurs between 8 and 13.5 microns. And this is a graph produced by GHG Lab of the integrated absorption spectrums. And what you're seeing there, those arrows that have percentages, and that black line. The black line is what I call, sufficiently absorbed that you might as well say it's, totally scattered IUs, or you could say totally saturated. It's near totally. If you go up higher to the next, it's a logarithmic scale going vertically. you get to 99.8, and then if you're up at the next one, you're 100.00, a few more zeros probably. So this shows you, this is one of the validations, and it's very useful also because over to the right, you see where it says 83.12%. This tells you how much of all the infrared radiation across the full spectrum gets intercepted by all the GHGs up through the atmosphere. That turns out to be useful. In some technical ways, I don't think I want to explain them today because I want to, in the interest of time. So, okay, this is radiative forcing. So scientists have been working on CO2 for a long time and come up with their radiative forcing level at 2.18. And in the one-dimensional mode of GHD lab, it's 2.17 by, could have been a few more off, a few more hundreds off, and still would have been good. I'll call that a coincidence, but it's a confirmation. This is a big confirmation. This is GHD lab, and if you look in the column B, I've unchecked all the boxes and I've done a run, and this shows that I'm coming within a few percent of that 33 Celsius that scientists both in Camp 1 and Camp 2 understand, and it can be measured by satellites and by Earth average temperature. So the fact that I'm within a few percent is an excellent confirmation. You would expect that if the atmospheric window was produced properly anyway. But and by the way, there's no other models that do that. I've not seen a model that produced an atmospheric window thing. People try to measure it, but they don't simulate it, as far as I know. And this goes with the accuracy thing and the fact that we're close to the total effect. So when you're out there at zero and you're within a few percent, as you come in with smaller changes in GHG, out at zero means I took away all the GHGs, went right down to level B was set to zero. But if I'm going to make an adjustment and go, certain amount up or down, back in time is down, and to the right is going up in time. It locks in the uncertainty because it's set to crosses the line right at 2023. So that's just a kind of a graphical representation of how the accuracy of the macro step of the 33 degrees is carried forward into smaller steps. This is another excellent verification, and GHG lab computes the water vapor feedback effect. And what I do, it was pure conjecture on my part. So when temperature goes up, the atmosphere can hold more water vapor. And what that means is that if you don't evaporate anything, the relative humidity goes down. And so what GHG lab did was I created a conjecture of probably the evaporation will bring it back up to no higher than what it was before. So when you go up by 0.78 degrees, which is the 2000 to 2023 years, the 24 years, that's NASA's temperature thing. That means that the relative humidity will go down to about 57% from 60. I set a default at 60. It's changeable. And then this is Met Office, UK office, historical average relative humidity across the planet. And what you see here is it drops by less than, a percent. You're looking at perhaps the black. There's different models here, but the black line or the green line or the blue line. And you're looking at to the right of how much, or to the left rather, how much percent drops less than 1%, maybe 0.5%, but it's definitely going down. And in GHG lab, it would go horizontally across. That's the conjecture. So it means that my water vapor feedback effect is slightly higher than what their measurements are, which is a good thing. It means it's slightly overestimating the feedback effect. I mean, it's not low, it's slightly high. And so that was an excellent confirmation of that complex effect. So computing the greenhouse gas effect, I'm going to skip through these really quick. We're on slide 42. The rest of the presentation is going to go really fast. This is where I got my absorption data for the greenhouse gases. Originally got about 180,000 data points for each greenhouse gas. And then I wrote a compression algorithm to keep the file size of GHG lab to a reasonable thing and validated that the compression didn't create any undue error. This is a supplementary thing. So the calculations are done between 3 and 20 microns. This is expressed in nanometers. So a nanometer is a billionth of a meter. A micron is a millionth. So it's times 1,000. So the GHG lab does the computations below what's showing 20,000 there, which is 20 microns. The reason we don't have to do any complex calculations above that is because we're in total saturation. You remember that line on that previous spectrum. It's at 100 point, huge number of zeros out, as it goes out towards 100,000 there, which is 100 microns. As I said before, all the data sets were available. And this is the one that tells you what the pressure, temperature, and density is going up through the atmosphere, created by NASA, NOAA, and US Air Force. And they have tables for different latitudes, and then they do a very nice averaging table. And that allowed me to set up this is the table that's used to calculate how saturated or how absorbed the infrared is going up through that atmospheric model. And this is just a distribution. This comes from another set published in 1986. And it's called Atmospheric Constituent Profiles, US Air Force Physics Lab, Geophysics Lab. And yet back before 1980, they had good understanding of CO2 and water vapor, which are the two important ones they could have used back then with a mainframe computer. I'm just going to mention this briefly. This is how I calculate the extrapolate out to 2001. And I want to make 2 points on population. So the UN has done modeling for population growth and has a number of models and projects that we're going to hit a population peak later this century and maybe as late as to 2100. And for various reasons, we're going to go into decline. Anyway, I'm not questioning their modeling and accepting that. And I guess the median predicted is by year 2300 will be almost a billion below what we are now. My point is that, I'm going to show how little the GHGs affect the rising temperature, and we don't really have to worry about doubling for reasons that it's not much of an effect. And you see up there have CO2, CH4, that's CO2, methane, and nitrous oxide doubling at 2141, 2177, and 2247. That's on the trend, but I don't think we're ever going to get there because of the prediction of the population going into decline. So all this worry about methane and nitrous oxide and CO2 staying in the atmosphere, we're going to hit an inflection point. The second point I want to make about population is I've been challenged in those 15 months of social media interactions. They've come back at me when they haven't had a good argument on the greenhouse gases. They come back with the thing, yeah, but we're too heavily populated. The planet's too populated. I guess the inference is that if we reduce the population, we're going to reduce the greenhouse gases and perhaps other things like pollution. And so I did a calculation. And this comes originally from that Malthusian thing about running out of food supply. So I did a calculation. I figured out with Google AI, how many ants do we have on the planet approximately, and what's the average weight of an ant? And turns out ants have a biomass weight of 8% of human biomass on the planet, and humans have fish have a biomass 12 times, or humans, let's say, are 8% of all the fish on the planet. And then when I go to the real question, what percentage of humans are what percentage is of human biomass compared to all the animal life on the planet? We're only 2.5%. And compared to all the plant and animal life on the planet, we're only 0.01%. So from a biomass point of view, we're not overpopulating the planet. Let me keep moving here. So in GHG lab, and this is a bit technical, I'll flip through these quickly, but there's 8 fitting parameters. And it's not fitted to match temperature or anything. It's fitted, the first 5 are to do with the distribution of GHGs up through the atmosphere to align the model to those distributions I previously showed, the constituent profiles. And the next 3 convert the GHG lab from a one-dimensional vertically up through the atmosphere to a 3-dimensional, which is what the atmosphere really is. And it took me a few months to figure out how I was going to do that, and then a few months to compute those parameters. They're esoteric, those 3 parameters, so you can't really get to the right one. So but you can do sensitivity analysis and prove that they're not too, the accuracy isn't too important. In fact, even between 3D and 1D, there's not a huge change. And that's because of that saturation. You saw that 83% I mentioned earlier. So we're fairly saturated already. And that puts a desensitization on some of these parameters. It puts a desensitization also on using averages for surface temperature and so on. And that's just showing those 3 esoteric parameters, the difference between 1D and 3D. I won't dwell on that. It'd be more for scientists to come back and talk to me about it. And this is how GHG Lab works computationally. I'm not even going to explain that one here. Again, it's there for a scientist to read. If they want to come back and have a discussion with me, they can. And now we're going to get into some revealing computations. And this is the one about the ocean temperature. So NASA and NOAA, and there's a company that made these Argo ocean robots. They're pretty cool things, actually. I was impressed. There's 3,000 of them floating randomly around through the ocean currents around the planet. There's some other probes and stuff that they measure, and they also do a satellite measurement on how high the ocean's coming due to temperature rise, which implies, how many joules of energy has been absorbed. And with the NASA satellite data I have, it goes from March 2000 to current. And when I did the calculations, so I studied from years, actually it's a slide here, I should have had 2023, which is it's 24 years in total. Anyway, I used I'm going to show you the calculations next, just as a flip slide, but NASA and NOAA, they have a difference of about, I think it's 10% or something like that. I'll show you those numbers. But I averaged their 2 numbers, and they come up with 2.26 times 10 to the 23 joules, a huge amount of energy that's been added to the ocean. And when I do my computations using the Ceres satellite, which is purely the rays going in and out of the planet, it's 2.13. So I'm coming right very close, which to be honest with you, I was very surprised that it's that close. Even if it was within 50%, I would have been happy. And those are the tables. So I'm not going to explain them other than to say this is an example of the resolution I get from those. These are real tables from the satellite that you can download, monthly tables. So I'm showing you how detailed or how much resolution they're providing. And this shows you 1 year. And what I do is I calculate the energy imbalance. So this is, just to explain it quickly, this is energy coming into the Earth. This is energy reflected. So the difference between these 2 values is energy absorbed. That's what these 2 values get. This is measured outgoing energy. And then when I take the difference of what's absorbed minus this, I get the energy imbalance for that month, which is pretty cool. And then you can see it's going down, it goes negative, and it goes negative, and then it goes positive. And the reason it's doing that is because the orbit of the Earth around the sun and the asymmetry in the absorption. We have 81% ocean in the southern hemisphere and 61% in the northern, plus we've got the snow and ice moving up and down in the northern hemisphere. And then, so that number there goes over for the year 2000. I just transposed it over there. And then I did similar calculations for every year. And then so that gives me the average energy imbalance over this 24-year period. And then I take the average open ocean area, And I take the seconds in that 24-year period, and you just do simple math here, and you can calculate how much energy got absorbed from a totally different method from all these probes and stuff that they got their numbers from, which is pretty cool. That's the two numbers. So NOAA has 2.15 and NASA had 2.37. And so this shows that the ocean heating has been dominated by the change in cloud cover, which I'll show you some pictures of that coming up. This is a calculation for the GHG warming the ocean, and I added so from GHG Lab I know what the rise of the GHGs, how much it adds heat to the atmosphere, its portion of the heat, and then I apply that to the surface of the ocean, and I generously go, surface at 18.5 and the 200 meters down you're at 4, and I do the simple thermal conductivity calculation, and there's a calculator around the web that does that for you, and then take the difference. And this is where I get over the right. The solar imbalance is 477 times more heat from the GHG rise, solar imbalance over the 24 from GHG over the 24-year period. So that's you can still find, if you Google, you're still going to find. I think NOAA is saying that rising GHGs are dominant or a main cause for the ocean temperature rising. This is the double CO2, including, I show two numbers here. When you double CO2 from the current, we're not talking about from the pre-industrial, so going from 421 in 2023 to 842 in column B, the GHG lab computes 0.50 Celsius rise. Over to the right, you see with the water vapor feedback effect at GHG lab, it raises it to 0.57. So a bit of a increase. Oops. This is doubling methane. Now this is in the presence of water vapor, and this is the significant thing. If I took water vapor out of there by unclicking the radio buttons around water vapor, those little check boxes, I would get a much higher number. I didn't present that here, but this is how insignificant methane rises. And this is a doubling of methane. And that doubling, if you follow the trend, I don't remember, I think it was year 2177 or something. And it probably is never going to get there. So we're fussing about killing livestock or reducing livestock for methane. And it's absolutely a ridiculous thing, because they haven't calculated the greenhouse effect properly. It's drowned out, as I said, by water vapor. Nitrous oxide, even though it's a lower concentration, it's a bit more potent. And this includes, so we're talking about, I think the year was 2240 or something for doubling of nitrous oxide. And if you include the water vapor effect, it's going to be 0.06 Celsius. That's affecting all the farmers with the fertilizer cutbacks and so on. Ridiculous. If I remove all the CO2 from the air, so this is a fictitious, there's natural CO2 and then there's, increases due to various things. But if I remove all the CO2, it's only a drop of, in the presence of water vapor, only a drop of 1.52 Celsius. This is removing, this is industrialization warming, going back to, I use 1750. It's almost the same as 1880, and then it starts to pick up. We have so I'm going backwards in time. So then it's a negative number. If I readjusted those numbers there, I would get a positive 30 degrees Celsius, including water. So that's the amount of heating, whether it's partially from, obviously we've contributed some emissions. Some people like to say it's 100% human. Other people would like to argue that, well, it's warmed up, so the ocean's releasing some CO2 and so on. It doesn't really matter to me whether it's 100% or not. 0.3 degrees Celsius is nothing. And keep in mind that a degree Celsius, if you look at the latitude going from equator to, say, the pole, on average, a change of 1 degree Celsius represent about 100 miles of latitude, which means that it really has no effect on plant and animal life. There's not going to be big migrations or anything like that. It's it's minuscule and we're adaptable. This is a fictitious thing where I take out all the methane and nitrous oxide, going back to a fictitious time where there's none, and that's never happened. It's only a 0.15 Celsius contribution to today's levels. And this is a quick thing. It's satellite data. These plots are interesting. This shows you Earth's energy imbalance, and you'll see, and you saw it in that data set that I showed you with the 1 year of year 2000. But you see it starts at around 6. It's a positive 6. And then it starts dropping, goes to a -10. And then it comes back up to a +10. And this oscillation is due to 3 things. It's the Earth orbiting around elliptically around the sun. So the sun, even though the sun is very constant in output, it's going from when we're in our winter, I believe in January, it's closest to the Earth is closest to the sun. And not only that, the southern hemisphere is at 80%, 81% water, and water is a very good absorber. There's very little reflection off it. So this is what's causing the oscillation and imbalance. It's the asymmetry of the absorption of the Earth. It's the snow and ice melting in the northern hemisphere, and it's the going around the asymmetry. Yeah, and that. So anyway, those 3 things are what's causing that. This shows Earth's outgoing radiation plotted against the variability of the sun on a year-by-year basis. So if you average out the year, that previous chart was showing monthly. So you got to see that waveform of it going positive, negative. But if you go year after year, you can see the trend. And there's a slight trend upwards with the outgoing radiation, meaning the Earth is getting warmer. And then plotted against the sun again, which is hardly wiggling, we've got the year after year trend in the change of the reflectivity. So it's going down. So the first thing I investigated was, what about snow and ice? There's a fair amount of snow and ice. It goes from, we don't worry about the southern hemisphere because you leave the poles out of it. But the only snow and ice moving, coming and going, is around the Andes mountains. It's very, very small surface area. But the northern hemisphere across North America and Europe is 50 million square kilometers when it's in a winter typically, and it's 2.5 or something like that. So it's a dramatic change in reflectivity. This shows the average, and you can see prior to about 1980, on the blue dots up there, they're a little bit above the line that says 2.5 times 10 to the 7th. That's 25 million square kilometers. Remember, this is the average snow and ice. And then once you get out, at 1980 and beyond, there's not much changing. Even though the temperature is going up, the bottom orange dots show the rising temperature, and the axis is on the right-hand side. So it's going below 14 up to 15 around the year 2023. And this is showing the net trend in annual snow and ice. So then this is the oscillation from around 50 million square kilometers down to 2 or 3 square kilometers. And it doesn't really change that much. It goes up and down. And I've done a linear fit line across the data, and it's almost horizontal. So what that says is, even though the Earth is warming, not much is changing at the surface of the Earth. So that's how we look at the clouds and know that the drop in reflectivity is coming out of the clouds and not coming from the warming and losing. We might be losing a bit of thickness of snow and ice. There's some other data I didn't plot here, but I plotted the week 15 or week 18 and was able to show that there was a drop prior to about 1980, or a rise prior to 1980, but it didn't affect the reflectivity area. It's just amount of precipitation. And this shows absorbed solar radiation plotted against the outgoing long wave. And you can see the phase relationship there. And I won't get into explaining that in the interest of saving time. Only got 5 more slides to go. This is expanding it for nearly 4 years. And there's 3 things plotted here. The orange peak is, or the orange line is the absorbed solar radiation. So that's the incoming minus reflected. The green line is the outgoing solar radiation. And the blue line is the snow and ice for North America. And there's some interesting things in the timing. You can see at the bottom, I've divided the year into a decimal, like 2022.83 is an example of one. So if you want to study this, there's some interesting, observations you can make with it, but I'm not going to dwell on that here. This is a very useful chart. This shows the year after year energy imbalance is growing and warming, and this is where you do that calculation and plot it. So everything above the 0% means it never goes negative on an annual basis. It's always adding energy into the system, supporting the calculations that I did for the ocean warming, and showing that there's a trend. And between the snow and ice records and the drop in reflectivity, we know it's a drop in clouds. And NASA confirms a drop in cloud, a protracted trend that's into decades. And that has been the cause of most of the Earth's warming. So the greenhouse gas and the feedback effects associated with that are about 15% of the trend upward. And the rest, the drop in cloud cover, has nothing to do with greenhouse gases. It might have a little bit to do with us cleaning up our emissions, but there's other things going on, as evidenced by the first 84 years of the dominant thing that's going on as mostly a natural phenomena. And this brings back the appeal to people that see this video is, I want to focus on early adopters and rounding up some scientists to help do the peer review. So anybody can introduce scientists that you think would have the aptitude, interest to do that. If you become an early adopter, definitely look for other people to join. I'm trying to build that early adopter, and hopefully we cross the chasm. It's not going to be done by debating with any of the establishment. It has to be done perhaps in the same way that the chasm was crossed with the Omicron. You can reflect on possible strategies I haven't thought of and communicate your ideas with me or others. Take some helpful action if you have some time to volunteer. That could be reaching out to build this group. I was impressed with the young fellow who took it on to redo my website. So if there's people with time on their hands and interest and perhaps connections, I am not a good marketer. I'm not a good salesman because it's just not my style. So if you gave me people to call, I'd call once probably. I get distracted by something else. I wouldn't do the follow-ups. So if you've got people that you think can help support this in any way, and you know them, you're better off talking to them and get them to reach out to me and tell me what they can do to help. That would be great. I'm interested in donations. I mean, it's a long haul doing 4 years of this, and if I get enough donations, I'll be able to possibly even hire some contractors to help me out that have the skill set that I lack. I'm trying to build enthusiasm in industries, and it would be nice if somebody working in any of those industries took it on to, I guess the word is recruit early adopters in the industry. I could envision somebody being keen and writing in an internal paper or perhaps an industry-wide paper a little story about this if they feel so inclined. That would be great publicity. I'm game to do a press release in an industry thing, but I like the industry to fund it and give me a professional marketing person to write the story, whether they're mentioned or not, or it's just a solo Climate Belt press release. And then I think investors that are sick of the ESG waste and distraction might be good ones to evangelize as early adopters, and who knows, they might even give me a little support as well. And that's the link over in the left-hand side for more grassroots information and donations. Oops, and this is the end. Finally, how long have I been talking? What's the
little under 2 hours, and this is
gee, it's I don't know if I've lost everybody, or I see a few people there, but
no, we still have 26 people who hung on. It's pretty good. I'm very impressed. And honestly, when we were in university, I remember having to sit down for 3 hour classes, and we learned a lot less than what you just presented.
Imagine how much more you would have learned if I kept it to an hour.
Oh. No,
anyway, I tried to go as fast as I could, and hopefully it didn't try to keep it interesting.
No, so, yeah, and I think that what you've done is established like a really powerful resource that I'm so glad is recorded. The slides were fantastic. It's worth revisiting and bringing up in meetings with people in industry especially. And
sorry to cut you off, but you see I'm on YouTube a fair amount. I haven't created any YouTube content. I posted my interview and my previous presentation just as a link. I may actually, on key areas of the science, I may make mini lectures, like a 5-minute or 10-minute lecture. So I'm trying to get people to. I'm not much. I have a Twitter account, but I'm not really. I don't do much with Twitter. It's not my thing. I'd use Twitter maybe to announce I got more followers on Twitter, not a lot, but than my YouTube. But I see YouTube as potentially being a place that I can. I've got a ragtag collection of useful videos. I just slap them into a playlist here and there. But someday I got to go through that and organize it. Whenever I watch a video that I think is useful, I throw it into one of my playlists. But it's not well organized. But
well, again, your climatebell.org site is very good. And Sean Good is asking, where can this video, this recording, be seen? Well, it can be seen in a few days. We're going to upload it onto the Rising Tide Foundation YouTube channel, like we do all of our lectures, and then also I'm sure Rodney's going to pop it onto Climate Bell as well.
I'll have it on Climate Bell, and I'll have it in one of my playlists on YouTube.
Great.
But again, I don't see the traffic on my Climate Bell. I used to have Google Analytics years ago, but it got too complicated. I don't have any analytics, so I don't know what traffic I got right now.
Don't worry about it. It's cool. So look, what we'll do, we'll open up for a little bit of Q&A. I'll kick it off. Actually, first, as you were speaking, Hans Schantz, who's here in the audience right now, and is a fantastic physicist and engineer, and he's produced some wonderful works. He's just volunteered to help out with the peer review project. So I'm going to put you guys in touch very shortly.
Excellent. Yeah.
So your roster.
Excellent. Thank you. And tell me, you're a physicist are you industry or academia?
In industry, not academia.
Good. I'm nervous for academics that are still publishing the repercussions, and I think it'd be difficult for them to fulfill the role that I want them to fulfill. So perfect. I come from an industrial. I call myself physicist/engineer, but we're free to do things that academics somehow get. I don't know, a little bit compromised with the politics on campus. Yeah, good, excellent. Thank you.
Quick question. I'll just launch you. I'll throw one question at you, and then Jenny's gonna have a follow-up question. Mine is regarding the actual causation of the cloud coverage, the vacillating cloud coverage. Does the work of Heinrich Svensmark and his work on cosmic radiation come into play when you're addressing what is the driving force behind cloud coverage, or are you looking at it in another way?
No, I because it's outside the scope of greenhouse gases and related feedback effects to greenhouse gases. I am not focused on that. I'm interested to hear. I know there's a few theories. One plausible thing, and I'm not sure what he feels about it, and it's really off topic for me, is we're orbiting the sun, and our solar system's moving through the galaxy at 200 kilometers a second or something like that. And with the water, with the temperature going up, I know there's more water vapor in the atmosphere. That's confirmed also, but with the Met Lab, with their RH only dropping slightly. So there's more water vapor, and there's two things with cloud cover. You have to have nucleation sites where water molecules can condense or freeze on, and you have to have more water vapor. Well, we got the more water vapor. We must be losing nucleation sites, and with that galaxy moving through, I'm not an astrophysicist, but it's plausible to me that there's cosmic dust out there that isn't uniformly distributed, and maybe we're coming into and out of bands of cosmic dust, and that could be, a variance in nucleation sites coming from one natural cause. I'd be surprised if it's not a variation in nucleation sites, because that's my simple-minded understanding of clouds. You get water vapor, and you've got to have the places for the water molecules to land on. But anyway, I'm interested, but not interested as a research thing. Interested as hearing, somebody's conclusion. Like I've presented conclusions here. I'm interested in a knowledgeable person, suggesting or proving what it is, and that's just it's academic curiosity. That's my interest level.
Cool, thanks. Jenny, it's all yours.
Okay. It's not a technical question. It's another name that popped into my head. If you're familiar with Denis Rancourt, by any chance?
I am not.
So he's a physicist out of the Ottawa area. I believe he was working at University of Ottawa, and I think maybe he got kicked out for daring to, be a heretic and question the whole climate crisis narrative. So since then, he works on his own. He's made a lot of parallels between the COVID pandemic, the way this, global cabal of elites are used the pandemic and are using the climate change crisis.
Yeah.
It just.
So he and I would share a coffee or a beer and enjoy an exchange. I'd be happy to meet him. I'm in Ottawa
exactly.
too. So
I saw you have a contact form on your website, so maybe I'll put you in touch with him through that.
Yeah, that'd be great. Yeah.
Cool.
Thanks.
Yeah, Denny, I think you'll enjoy his site and his work. He's done a couple of presentations for us in the past, and it's impressive. I think you guys will hit it off. But I got another question too regarding something I had heard. So it's sort of a twofold question. I had heard some years ago, back in 2012, 2013, there was talk of a global warming pause that had been going on for 20 years. And then it kind of got scrubbed from the internet as if it didn't happen. But I've gone to the Wayback Machine, and they were talking about this. And so that's one question: is did you look at this global warming pause anomaly thing at all? And number two, okay, then I'll have another follow up. I'll let you.
Yeah. So my thing is to, as best. So here's my thing with data sets. I have not found a data set that I object to. I have used establishment data sets. I have immense respect for the data set people, the people that design the instrumentation, the people that collect the data and preserve the data. There might be a little bit of urban heat out in the fact I've been communicating with NASA as just not identifying myself as Climate Bell, but I've got an email from about a week ago on trying to pin down the error bars for the monthly accumulation or something like, I can't remember how many, 100,000, is it a day or an hour measurements that go into those monthly values that I download. So I'm trying to get the 2 sigma uncertainty around those 6 digits of or 7 digits of that I showed you there. Where I don't care is time period before industrialization. You're talking about something 2012, where if there has been a plateau, I'm not seeing it in the data set that I use, and even if there was the Berkeley Earth that did an investigation around 2010, and that data set didn't come out with any startling errors. Even if there's urban heat island effect there, I don't think that NASA Goddard Space Center data set of temperature has been deliberately tampered with. And the reason I say that, and it's conjecture on my part, the reason I say that is if they wanted to deliberately do something to fake it, wouldn't they have removed those things that I call the region of evidence? Like they left them there, right? And the thing, they basically, and I've dealt with thousands of people on social media on that thing. Nobody's been able to refute it. They just get angry and tell me I cherry pick data, or I'm making it too simple, or it's more another way of saying it's more complicated than I'm making it. But anyway, so I'm respectful even of the temperature data set because they left me the evidence. So it could have been a plateau that somebody fiddled with in the latter part of the data. That's possible. But unless I have evidence of it, I'm not going looking for it. But I'm interested when there's discrepancies. Like if there's another data set out there, I'm interested. Could that have been a data set more regional, say to the North American continent or something, as opposed to the global thing? I don't know. I've got the NASA in, out, and reflected stuff. I should be able to see it there, right? And I'm not seeing it.
The follow-up question I have, and thank you for doing that, for saying that. It's very nuanced and good.
Yeah.
I had read some years back, and I always thought that I was going to be able to find this article again, and it was not so easy, but it was describing the reduction of the distribution of the CO2 monitoring stations. I guess maybe more broad, they might be monitoring more than CO2, but that the distribution of them was more balanced between urban centers and rural centers in the 1950s, 60s, 70s. And then something happened in the 80s and early 90s where the rural monitoring stations were, or a disproportionately large amount were eliminated, leaving principally the urban monitoring stations disproportionately represented where it gets hotter. And I'm wondering if that's something you had also encountered as far as,
are you just to clarify, you're talking about CO2, not temperature. Are you talking about temperature?
Oh, sorry, temperature.
Okay, good.
Not
okay.
CO2, sorry.
Yeah. Okay. So this is the urban heat island effect, and basically, I don't know. So again, I'm taking that temperature record and doing computations on it. What I see in the, so this is stuff I haven't published and I'm still investigating it. But if I plot the incoming in the absorbed solar radiation against the temperature record, it lines up perfectly. Well, not perfectly, but it wiggles around the temperature record. But it's really the outgoing one that's the one you want to pay attention to, because you've got the average surface temperature, and then you've got the emission to space, which is your outgoing, and that one's dropping. So in other words, the temperature record is separating higher from the computation of the greenhouse effect and the outgoing. It's hard for me to assemble the words to say it properly, but anyway, I'm seeing a gap, and I want to see if that's the urban heat island effect, but I need those numbers on the error bars. I have no error bars. I have these very high resolution monthly numbers with no error bars. The literature, the specifications on the satellite stuff, it doesn't look very impressive, but the amount of digits I get in my monthly suggests to me that it is. And there's wording in that email that came back from NASA that alludes to it. It's accurate, but I have to go off to some sources. I think they're reports somewhere on, might have been a paper, but I think it's reports somewhere. She's listed, or they've listed 3 things for me to go after and where I should look to find it. I got to see if I can get it, but I've been busy with this and other things, so I haven't had a chance to go off and dig and then do calculations again. It's on my to-do list, but it's not like a burning issue for me right now.
Yeah, pun intended, I'm sure.
Yeah, I didn't mean a pun, but it's good. Sometimes puns come by accident. That was an accidental pun.
All right, Pamela's got a bit of a controversial one for you. Pamela, Go for it.
Hi, Rodney. I'm in Ottawa. I'm also in Ottawa, And I'm
Nice.
also one of those ex-BNR people in Ottawa.
Oh, cool. Very cool.
Yeah. And I keep hearing whenever we have forest fires in the summer, I keep hearing little comments on the news that the forest fires are related to global warming. And I find it difficult to accept that, because I think the spraying of glyphosate or something like that is a much more likely cause
Mhm.
than global warming. But do you have any comments on that one, like, or evidence or reasons I could use to say?
Well, no,
Yes.
I mocked it in this presentation, and
Okay.
did you see that little part, or did you step away?
No, I
Oh,
didn't notice.
okay. There, if when you watch the rerun,
Okay.
no, it was one of the mocking things of. There's a whole bunch of other causes, but at 1 degree Celsius, I mean, it's possible that the climate shifted, and California was dry and now it's wet, and somewhere out west was regular moisture and had a bad year or 2 bad years of dryness. But that's one of the logical reasons. They were in that part of the presentation, which I spoke for like 30 seconds. I listed the fact that there's certain bugs that get into a forest of trees and kill them off, and you've got standing deadwood that's never cut down. You've got brush underneath that's never cleared out. You have arson as well, and you have droughts that create a very dry tinderbox. So those are more logical reasons for forest fires, not that the temperature went up 1 degree and it's not really any closer to combustion yet for that. So, yeah. Thanks for the question, though.
All right, we're going to open up for one last chance. If anybody's got a question they want to get off their chest, now is the time. We have a small window remaining, but it's a very small window. So
I have a question.
Oh, yeah, sure.
That list of 20 things I did, the correlation of behaviors. I don't know what people thought of that. Was that something I should not be mentioning again? Or
No,
was that?
It's good. It's punchy.
Okay.
All right. Monty, I saw your digital hand go up.
Okay. Yeah, I'm finding that there's a whole market that's developing to monetize this whole CO2 with carbon trading, and I see this as very dangerous. You would be monetizing for profit. In other words, basically to kill people is what you're gambling on. And given the AI and the cybernetics and the twisting of things, I can see how this could become very popularized. Do you have any comment on that, or what's your opinion in that regard?
All the schemes to carbon trading and carbon capture programs and stuff. To me, the people that are, buying carbon credits to fly, I'm sure the perpetrators of the hysteria own shares in those companies. So even if they grandstand, say, hey, I buy carbon credits for all my jet flights, they're giving money to themselves. They're a major shareholder. So I'm not a fan of those things for the reasons that it's profit at somebody else's expense, and it's baseless. I'm very frustrated with the farming attacks that have gone on. Somebody come and prove me wrong with the absorption spectrums. Come and prove me wrong. I'm challenging, the ECS method and the radiative forcing. That's a method that belongs in the 1970s, right? That does not belong with the satellite data we have. There's a thing in math and science and engineering called how specified is a problem. It's underspecified is you're needing more information to solve it. Overspecified means you have contradictory data that you have to now figure out where the bad data is. And properly specified, I think that's the term, properly, fully specified. That means you've got all the pieces that you need to put it together and do the calculations and solve the problem. And what's neat is the problem of solving the rising greenhouse gases, if you do your model right, it's been fully specified since 1980. And the solution to understand the cause of the changes in temperature has been specified, fully specified from the data set from the year 2000 to to current, let's say we have 25 years of satellite data that reveals, and that's why I'm impressed with the people that made the equipment and the people that maintain the data. Is I don't think they're not on the wrong side of the fence. They're doing their best, and there's integrity. It's the weirdness that happens. The people that spin the thing without doing the calculations, or they don't want to do. Is it reckless negligence, or is it deliberate deception? I'm just, it's really pathetic. Those are the people that I don't know what to do. Yeah. So that's why if somebody has a better idea than the crossing the chasm thing, please let me know, or please implement it. I'm equipping people with the evidence that they need to win. Is what. But we have to have a strategy, and I don't think I'm the best person at strategizing or marketing, or as evidenced by my old man's website before that young guy came along and go, I'm going to help you. I needed the help, and I couldn't even see I needed it. That's how bad it was. So I thought it was a good looking website, but not at all. So yeah. So apply your talents. I've tried to do mine. Apply mine. So if people have talents in marketing or networking, my wife would be happy if sooner or later some support comes in. She's carrying the bills these days. So
right.
And but she's cutting me slack, right? Because she sees the importance.
Well, I think also the idea too of like AI, a positive use of AI would probably, I could see it very clearly in terms of just keeping all of these data sets, not just updated, but all of the work you've done to come up with your charts and everything else, so that you could have a very quick upgrade to 2024, 2025, 2026, and just immediately put all the new data through calculations to keep your these very potent resources as up to date as possible. I'm sure it takes a lot of work, an immense amount of work. So maybe AI could help to accumulate the data, do the calculations, so you don't have to.
Maybe there's somebody out there that I can give them the data and they can spit out a video, so I don't have to sit there and record myself trying to put together might turn out just as bad as my previous website, right? So if somebody has a talent and they say this is the information I can put into a mini lecture, that'd be great.
All right, so that's a call to action. So anybody watching this on YouTube or anything, go to the description box under this video, find Rodney McInnis's contact info, which will be in the description box, including the website. So reach out if you have skills and passion and want to help out. Hans is already on board. So Rodney, I just want to say thank you so much for taking the time and sharing your wisdom and knowledge. Appreciate that so much. And thank you everybody for joining us for this week's Rising Tide.
I'm very thankful for people to stick with it for 2 hours, and I thank you for your kind invitation. So I really appreciate it.
All right. Take care. Bye, everyone.
Thank you. Bye-bye.